This code imports all the dependencies that are needed for the code to run correctly. First, it imports NumPy, which is used for numerical computing. Then it imports pandas, which allows for the creation and manipulation of data frames. Next, it imports matplotlib, which is used for data visualization. This line ascent matplotlib inline ensures that the plots are displayed directly in the notebook. The code then imports color maps from matplotlib for further customization of the plots. Finally, it imports Seaborn, which is a data visualization library that provides an easier way to create and customize plots. First, we import the matplotlib library, which allows us to create visualizations in Python and customize their properties. Then we also import the Seaborn library, which is built on top of matplotlib and provides additional data visualization capabilities. We set the figure size to be 9 by 4 by using the pl.figure function. This determines the size of the visualizations we will create. Next, we use the counterplot function from the Seaborn library to plot a bar graph of the emotion column from the data frame df. The x parameter specifies that we want to plot the counts of each unique value in the emotion column. Overall, this code sets up the environment to create a visual representation of the number of occurrences for each emotion category in our dataset. This code creates a figure with a width of 9 and a height of 4. Then it creates a count plot using the usage column from the data frame df. This plots the frequency of each category in the usage column as bars on the graph. The figure size specified ensures that the graph is of appropriate size to display the data clearly. This line of code imports the OpenCV library and allows the user to use its functions and methods. The next line sets the size of the image in pixels to be 48 by 48. This is the standard size of images used in facial recognition tasks. This code takes a dataset, specifically the pixels column, and converts it into a list called pixels. The next few lines of code initialize the size of the images to be 48 by 48 pixels and creates an empty list called faces. Then, it loops through each element in the pixels list, splitting the string by spaces and converting it into a list of integers for each row. These lists are then converted into arrays of size 48 by 48 and resized using OpenCV to have uniform dimensions. These resized arrays are then appended to the faces list. The faces list is then converted into a NumPy array and expanded to have an additional dimension representing color space. Finally, the emotions column from the dataset is one-hot encoded and converted into a NumPy array, which will serve as the labels for the images. Overall, this code is preparing the dataset for further processing and analysis, specifically for emotion recognition tasks. This code prints out the first item of a variable called faces. Faces presumably contains data or information that has undergone some pre-processing before reaching this point in the code. The result of this command would be a display or description of the pixels that make up the face. It is not clear what specific pre-processing steps were taken or what format the pixels are displayed in. This code first prints the shape of the dataset faces, which represents the dimensions of the dataset, including the number of rows and columns. The next line prints the number of dimensions of the first element in the dataset using the .ndm attribute. The last line prints the type of the dataset, which is a NumPy array. The given code prints the element at the first index of the emotions list. It retrieves the first emotion after it has been pre-processed. This means that the text or data has been transformed in some way to make it easier to use, often by removing unnecessary information or changing the format. This code is performing a series of operations on a variable called emotions. The first operation is printing the shape of the variable, which determines the number of elements in each dimension. The next operation is printing the number of dimensions of the variable. Finally, the code is printing the data type of the variable, which determines how the data is stored and what operations can be performed on it. Overall, this code is providing information about the size and structure of the data contained in the variable emotions. First, the code converts the data type of variable faces to float 32. This allows for more precise calculations later. Next, the code divides all values in the x variable by 255. This is done for normalization, which scales the pixel values in a range of 0 to 1. Then the code subtracts 0.5 from all the values in x. This shifts the range of values to a range of 9.5 to 0.5. Finally, the code multiplies all values in x by 2.0. This expands the range of values to megas 1.0 to 1.0. This overall process of dividing, subtracting, and multiplying is known as feature scaling, which aims to improve overall model performance by ensuring all features are on a similar scale. This code prints out the first element of the variable x. It is accessing the first index of the variable and printing it to the console. This could be a string, list, or any other data type. This particular code does not assign the value to a new variable or change the original X variable in any way. It simply retrieves and displays the value at the first index. This code creates a line plot with the given data and displays it using the show function. The data is located at the first element of the X array, which is located at the first element of the first row. This code prints the minimum and maximum values of the variable X. From the comment, it appears that these values correspond to pixels that are part of an image. The minimum value is 45, meaning that the lowest intensity of pixels in the image is given by this value. The maximum value is 255, indicating that the highest intensity of pixels in the image is represented by this value. This code gives us a rough idea of the range of pixel values in the image, which can be useful in understanding the overall brightness and contrast of the image. This code essentially divides the given dataset into training and validation sets. The first line of code calculates the maximum number of samples and classes in the dataset. The next line assigns numSamples variable with the length of the dataset. The third line calculates the number of training samples by removing 20% of the total samples from the dataset. The next two lines create two variables, train X and train Y, which contain the first numTrain samples number of samples and corresponding emotions from the dataset, respectively. Similarly, the next two lines create two variables, val_x and val_y, which contain the remaining samples and emotions from the dataset. Finally, the last two lines create two tuples, train data and val data, which store the training and validation sets, respectively, for later use in the code. This code first prints a message training pixels and the shape of the train X dataset, which refers to the dimensions of the dataset, including the number of images, width, height, and color. Then, it prints messages and the shapes of the train Y, val_x, and val_y datasets, which represent the label data for the training and validation sets. The shapes of these datasets indicate the size and structure of the data, providing important information for further analysis and model training. First, we import the necessary libraries to build our model using the Keras library. These libraries include layers from convolution, pooling, activation, batch normalization, dropout, and so on. Next, we define the model architecture by creating a sequential model using the sequential class from the Keras library. Then, we import the necessary layers, such as flatten, input, max pooling, and separable convolution layers. These layers will be used in the creation of our model. We also import the L2 regularizer from the Keras library, which helps to prevent overfitting of our model. Overall, this code is setting up the necessary tools and building blocks needed to create our model using the Keras library. This code creates a model called sequential and adds layers to it. The first layer is a convolutional layer with 16 filters, a kernel size of 7 by 7, and a padding of same. This layer is named image array and takes in an input shape specified by the input shape variable. Batch normalization is then added to this layer. Following this, another convolutional layer with 16 filters, a kernel size of 7 by 7, and a padding of same is added, along with batch normalization. An activation function of ReLU is then added. This process is repeated for two more sets of layers, with different filter sizes and pooling sizes. Finally, a convolutional layer with 256 filters, a kernel size of 3 by 3, and a padding of same is added, along with batch normalization. Another convolutional layer with a number of classes as filters and a kernel size of 3 by 3 is added, followed by a global average pooling layer. The final layer is an activation layer with softmax as the activation function and is named predictions. The model.summary function provides a summary of a machine learning model. It displays the different layers of the model, the number of trainable parameters, and the output shape of each layer. It also shows the total number of parameters in the model and the number of parameters that will be updated during training. The summary helps to get an overview of the model and the flow of data through its layers. This code sets up the parameters for a simple convolutional neural network CNN model used for classifying emotions in images. These parameters include the batch size, which is the number of images used to calculate the gradient for each update during training, the number of epochs, which is the number of times the model will go through the entire dataset during training, and the input shape of the images expected by the model. The code also sets up other variables such as the verbosity level, which determines the amount of information displayed during training, the number of classes being considered in the classification task, the patience level, which is the number of epochs that the model will continue to train even if there is no improvement in performance, and the base path where the model and its results will be stored. This code will help to ensure that the model is properly trained and can accurately classify emotions in new images. This code imports different libraries and packages that will be utilized in the code. The first import statement imports CSV logger, model checkpoint, and early stopping callbacks from the Keras library. These callbacks will be used to track the training process, save the best model, and stop the model from training if it is not improving. The second import statement imports the reduce aileron plateau callback, which will reduce the learning rate if the model is not improving. The last import statement imports the image data generator from the Keras library, which will be used to generate batches of image data for training the model. The code above performs data augmentation, which is a technique to increase the generalizability of a model by applying random transformations to a batch of tensor image data. The data generator allows for real-time augmentation, meaning the transformations are applied as the data is being processed rather than pre-processing. The transformations applied include rotation, resizing, and shearing, which helps the model to better understand and classify images that may have different orientations or sizes. Additionally, features like feature-wise centering and standardization are disabled to prevent overfitting. This data augmentation technique helps to improve the performance and accuracy of the model. This code creates a neural network model for classification and sets the parameters for the model. The first line specifies the optimizer, loss function, and evaluation metrics to be used. In this case, the optimizer is ADAM, which is a popular gradient descent optimization algorithm. The loss function is categorical cross-entropy, which is commonly used for classification, and the evaluation metric is accuracy, which measures the percentage of correct predictions. The next line compiles the model using these parameters. Finally, the code prints a summary of the model, including the layers, parameters, and output shape. This summary can be used to check if the model has been built correctly and to get an overview of its architecture. This code is used to train a neural network model on a dataset called FIR 2013. The dataset is located in the directory content. The code uses a for loop to iterate over all the datasets. In this case, only the FIR 2013 dataset is used. During training, the code will print the name of the dataset that is currently being trained. The code also creates a log file to keep track of the training progress. It then sets up callbacks for the training process, which includes early stopping and reducing the learning rate if the validation loss does not improve. The trained models will be saved in a directory called simplecnn. The code also creates a list of callbacks and passes it to the fit-generator function, which trains the model for a specified number of epochs. This code is evaluating a machine learning model and printing out the test loss and test accuracy. The evaluate function is being used to calculate the loss and accuracy of the model using the validation data. The results of this evaluation are stored in the variable called score. Next, using the print function, the code is displaying the test loss and the test accuracy on the console. The test accuracy is being multiplied by 100 to convert it into a percentage for easier interpretation. This line of code prints a value from the accuracy key in the dictionary called history_dict. It accesses this value by using square brackets and the key name in quotes. This dictionary likely contains information about the accuracy of a model or code over a series of iterations or epochs, and this line specifically prints the value associated with the accuracy key. The code begins by importing the matplotlib library, which is a visualization library in Python. It then creates two lists that store the training loss and validation loss values from the history dictionary. It then creates a list of epochs based on the length of the accuracy values from the dictionary. The next few lines plot the training loss and validation loss values on a graph using the matplotlib plot function. The plt.title, plotxlabel, plt.ylabel, and pl.legend functions are then used to add a title, axis labels, and a legend to the graph. Finally, the pl_show function is used to display the graph. Overall, this code is used to visualize the training and validation loss values over the course of different epochs to help understand the performance of a machine learning model. This code is plotting the training and validation accuracy over the different epochs of a model's training process. It first extracts the training and validation accuracy values from a dictionary called history_dict. Then, it uses the plot function from matplotlib to plot the training accuracy as blue dots and the validation accuracy as a solid blue line. The title, xlabel, ylabel, and legend functions are used to label the plot and make it more understandable. Finally, the plot is displayed using the show function. Overall, this code is visualizing the performance of a model during training by plotting its accuracy over time. This code creates two dictionaries, one to map numbers to emotions, and one to map numbers to corresponding emojis. The first dictionary is called Emotion Score Dict, and it assigns numbers 0 to 6 to different emotions such as neutral or happy. The second dictionary is called Emojis, and it assigns numbers 0 to 6 to different Unicode values that represent emojis. These dictionaries make it possible to associate specific emotions with specific emojis, allowing for easy access and use of emojis in a code. This code prints the values of the emojis dictionary, separating each value with a space. It disregards any comments and just prints the values in a single line. The values method retrieves the values from the dictionary, and the set parameter controls the separator between each value. In this case, it is set to a single space. This code changes the current directory to the content directory, then displays the current directory path and lists the files and subdirectories within the current directory. It uses the built-in terminal commands cd to change directory, pwd to display the current directory, and ls to list directory contents. This code is using the har cascade classifier to detect faces in an image. It starts by importing the necessary libraries and defining a function called predict that takes in a path parameter. The path is used to access the image to be analyzed. The image is then read and converted to grayscale. The next step is to use the facecask.detect multiscale method to locate any faces in the image. The number of faces found is then printed. Next, a for loop is used to iterate through each face found and draw a rectangle around it. The region of interest ROI is then cropped out and resized to 48 by 48 pixels. This cropped image is then passed into a model for prediction. The highest probability is then taken and used to index into a dictionary to find the corresponding emotion. This emotion is then printed onto the image and displayed using the cv2imshow method. This code is predicting a label for the given image that is referred to as me.png. The image is likely stored in the images folder, and the code is using the predict function to make a prediction based on the image data. The exact prediction method and algorithm will depend on the specific code being used, but ultimately the code is attempting to assign a label to the image based on the data it contains. The code executes a function called predict using an argument of images tr.jeg. This function is likely part of a code that creates predictions based on input images. The argument images tr.jpg is likely the location of a specific image file. The predict function likely utilizes an algorithm or machine learning model to analyze the given image and produce a prediction. The purpose of this code is to generate a prediction for the given image file. This code is called predict and takes in an argument called images mb.jp. It is likely used in a machine learning or artificial intelligence context, where it will use some sort of algorithm to make a prediction based on the input image. The specific purpose of the prediction is not clear from this piece of code, as it only specifies the image and not the desired output. Based on the file extension JPG, it is likely that the image is a JPEG file. The prediction could range from identifying objects or patterns in the image to determining the likelihood of a desired outcome based on the image. Without further context, it is difficult to fully explain the purpose of this code. This code takes an input of an image file, specifically an image of actor Ram Charan in the .webp format, and predicts something about it. The first step is to load and pre-process the image, which involves converting it into an array of numbers that can be interpreted by the model for prediction. Next, the code calls on a pre-trained model to make its prediction, using the processed image as input. The output can be in the form of a label, a probability, or both, depending on what the model is designed to predict. This code can be used in various applications, such as image classification, object detection, or facial recognition. This code is used to predict what object or image is being shown in a given input image, such as cons.jpg. It is likely part of a larger code or model, as it is only a single function call. First, the function predict is called with images cons.jpg as its input parameter. Inside the function, there is likely code that loads and prepares the input image for prediction. Then, the model or algorithm within the function uses its trained data and parameters to analyze the image and make a prediction. The output of this function is likely the predicted object or image, which could be cons in this case. Other parameters or variables may also be used in the function to fine-tune the prediction process. This code is calling a function named predict, passing in the file path images me3.png as the input. This function likely takes in an image file path, loads the image, and uses a model or algorithm to make a prediction based on the image data. The exact purpose or output of the prediction is not clear without more context. This code imports the image function from the ipython.display library, allowing us to display an image. It then displays the image stored at the specified location using the image function. This code saves the weights of the current model in a file called model.h5. These weights are numerical values that define the parameters of the model. This is important because it allows the model to be reloaded and used later without having to retrain it. The .h5 file extension indicates that the file is in hierarchical data format HDF5, which is a data format commonly used for storing and managing large data sets. Saving the weights in this format ensures that they can be easily retrieved and used for future predictions or training. Overall, this code is a crucial step in the model building process as it saves the learned parameters for later use. This code loads the weights of a pre-trained model that is stored in a file named model.h5. Loading the weights means that the model will have the same set of parameters as when it was last saved, so it can continue making predictions or learning without starting from scratch. This is useful for saving time and resources when reusing a model for new tasks. This code imports a function model from the Keras library called model from JSON into the current code. This function is used to create a neural network model from a JSON format file. Importing this function allows the code to access and use it for creating and training neural networks. This code is used to save and reload a model so that it can be used at a later time without needing to retrain it. First, the model is converted to a JSON string using the toJSON function. Then, this JSON string is written to a file named model.json using the W flag to indicate that it is being opened for writing. This file will contain all the necessary information about the model's architecture, but not its weights. Next, the weights are saved to a separate file using the saveWeights function. After printing a confirmation message, the code then moves on to loading the model. It opens the model.json file and reads its contents as a JSON string. Then this string is passed to the model from JSON function to create a new model with the same architecture as the original. Finally, the weights are loaded into this new model using the loadWeights function, and the model is ready to be used for predictions. This code imports the necessary libraries for downloading files from Google Colab and specifies the files that need to be downloaded. The code then calls the respective download functions for each file, saving them to the user's local computer. This ultimately allows the user to easily transfer files from Google Colab to their own computer. This code takes in an array of numbers and a count parameter. It then uses a for loop to iterate through the array and compare each element to the count parameter. If the element is equal to the count, the loop breaks and returns true. If none of the elements are equal to the count, the loop ends and returns false. This code essentially checks if the count parameter is included in the array of numbers. This code creates a function named diffArray with two parameters, r1 and r2. The function first creates a new empty array to store the different elements from r1 and r2. Then, it loops through r1 and checks if r2 does not include the current element. If it does not, it adds the element to the new array. Next, it loops through r2 and checks if r1 does not include the current element. If it does not, it adds the element to the new array. Finally, the function returns the new array with the different elements from AR1 and AR2. Overall, this code compares two arrays and returns a new array with any unique elements present in either of the original arrays.